Hello. Let me welcome you here in Showmax offices again on another WeStream meetup. Today we'll be speaking about ultra low latency for live streaming and live of live streaming, and then live of the movie and what will happen about with any movie that we will get from the studios before people will start playing it. So it's actually the best part of streaming of videos, I would say. And with this, Michal will start from CDN77 speaking about ultra low latency with live streams.
So hi, my name is Michael. And as was said, I'm with CDN77. And today I would like to present to you a summary, short presentation about how to do live latency, live streaming over HTTP. So first of all, when we talk about latency and low latency, what are we talking about? Usually when we talk about latency with live streaming, we are talking about end-to-end or sometimes called glass-to-glass latency, meaning how much time does it take between something happening in front of camera till user can see it on their screens. And when we talk about low latency, we usually talk anything between 5 seconds. And ultra low latency with this is usually sub-second. For comparison, normal live streaming over HTTP is usually 20 to 40 seconds. And to put it in perspective, normal broadcast, normal TVs are usually 4 to 6 seconds. Why do we need low latency? Well, there are two main reasons you will find. The first one is sports. You probably heard that. You want to see the goal before you hear your neighbors that they scored the goal. So that's a big one. And the second one that's starting to be more and more important are social networks. More and more social networks today implement live streaming, and people want to interact with the audience. And having 20 or 30 seconds of latency is not great for that. So we try to make the latency lower than the 5 seconds. And also it's cool, it's just a cool demo to be able to transfer video that fast. Sorry. Well, I'm gonna have to live with that. To get everyone on the same level, or what we are even talking about. What's HTTP? The important point for today's talks is its request response protocol. It's the protocol underlying current or all web technologies, and it's usually somewhat file-based, meaning user requests some file from a server, and the server responds with file data. Problem with any request response server is request response protocol is how to scale that. The two main points you will hit with that is how to handle server loads and how to handle latency. How to handle latency when a user is on the other side of the world than the server. And the classic response to that is use a CDN, which is just usually just putting proxies between the origin servers, meaning the servers that contain the data and the users. The servers can handle part of the load and can be closer to users. So okay, we have HTTP protocol that's widely used, and we have CDNs. We have the infrastructure how to scale that. So how we do live streaming about over HTTP? Currently, there are two main technologies in use: HLS, which means HTTP live streaming, which is from Apple, and MPEG-Dash, which is ISO standard from the MPEG group. And both of them work in the same way. When they split up the video into video segments, each segment representing like 2 to 10 seconds of the real video, and then they put the list of those segments inside some index manifest. Sorry. So the client requests a manifest from the server. That manifest contains a list of the segments, usually contains other info about the live stream. Both of those protocols support adaptive bitrate, meaning multiple bitrates, multiple qualities, multiple resolutions can be provided in one index or manifest. The client downloads that, decides which quality it wants, and then downloads the media files. This is the same for streaming of VOD. and live streaming and live streaming. The main difference being that for VOD, the index is static, so it can be downloaded only once. For live streaming, we usually have to refresh the index, so those two steps are in loop. You download the index, see which media files need to be downloaded, download the media files, and refresh the index again. So, okay, that describes how to deliver the segments at the end, but how do you create those segments? Usually the pipeline for live streamings look somewhere like this. When you have the source, which can be from mobile phone to some bigger broadcast production. Then you have the processing part, which is from the ingest to the storage. And then you have the delivery part, which is from origin to the client. From the source, we get the raw video. On the transcoder, it's created into usually multiple resolution bit rates and prepared for the adaptive bitrate. Packager will be very interesting for us today. That's the place that from the raw video creates the segmented video files and creates the manifest/index for the HLS or dash streaming, and then it's delivered as normal files to the users. So where does the latency come from in this setup? If we look on the numbers I put there, the biggest numbers are the segment duration above the storage and the read-ahead buffer at the client. So how do we address those problems? Or where does the delay or latency with segment duration come from? This graph shows time from left to right. And we can see the packager creates a segment, uploads it to the origin, and client can then fetch that. A packager then starts creating a new segment. Let's say it waits 5 seconds before it collects the data for the 5-second segment. And only that uploads it to the origin, and only that the client can fetch that. The biggest latency problem here is the packager got some frames at the start of the next segment here, but client can play them only after fetching them there. So if this is 5 seconds long, at least those 5 seconds of latency are added, and there's nothing we can do about it from the technical point of view. The simple solution would be just make the segments shorter. And that's a perfectly valid solution. People do that. From 5 seconds, you can go to 1 second segments. But when you start to going to 2 seconds, 1 second segments, or sub-second segments, you start to hit overhead of HTTP, and you start to hit problems with inefficiencies of the codecs. Overhead of HTTP means every segment means new request and response over HTTP, which means new data needs to be processed above the video files. And codecs overhead means that segments usually should be playable by themselves. That means that they should have a closed GOP, group of pictures, which means they should start with keyframe. Keyframes take up a lot of space, and we usually set up GOP at transcoder to like 2 seconds. It's like one of the industry standards, 1 to 2 seconds. Means every 2 seconds, create a keyframe. When you start going below that, you are taking a lot of space by the keyframes, and you doesn't have enough quality to leave for the other frames. So when you create shorter GOPs, your compression ratio and your quality will go down. And when you decide to create segments smaller than than 1 second, you are forcing GOP to be smaller than 1 second. You are forcing keyframe to be every, let's say, 500 milliseconds. So the other solution is, and I'm sorry for this image, I had no idea how to do it better. You doesn't have to wait before the segment is fully created to send it to the client. Because actually with MP4 and H.264 codec, you doesn't have to have full segment, full file, before it can be decoded and played. So what you can do is, as soon as the packager starts creating a new file, the file is presented to the origin, and it's presented to the client, which can fetch it. So as soon as it starts, the client can start fetching it, decoding it, and playing it. playing it. So we are shortening this delay to something very small. It can be under 100 milliseconds or even under 50 milliseconds. It's practically limited to the network round trip time. The problem we still will face here, and I will talk later how to solve that, is if we use the classic HLS, when we just put a list of the segments to some playlist, we still have to wait and refresh the index before we can start downloading the file. So we are still creating some delay between fetching index and start of fetching the media. Anyway, going with this, the important point being we need to support the transfer here, which we with HTTP can. HTTP 1.1 supports so-called chunked transfer that allow us to download the file before it's fully created and before we know the file size. Also, it requires support for the packager, origin, and client, but it very much lowers the latency. So this is the way the industry chose to do low latency over HTTP. There is a solution on the Dash side called low latency modes for Dash. That was first drafted in 2017, and currently we have the last draft from March 2020. I'm sorry, don't quote me on that. I am not sure if it's actually now a merged ISO standard. I didn't want to buy another ISO standard. That's one of the problems of MPEG Dash. It's those standards are paid. So you can't read the standards for free, but you can read the change request, which is currently stabilized and widely used. And low latency Dash brings us two things. One is support for the chunk transfer and chunk encoding. The second one, low latency Dash addresses how to minimize the latency of fetching the index and fetching the media. Low latency Dash or Dash in general supports so-called segmentation template, and that allows us for the index not to be just a list of files, but it can be just instruction in form of the live stream started today at 12:30. Every segment is 5 seconds long. The segments are numbered from number 1, and you can find the segment at path/abc/segment number.mp4. So client can fetch the index only one, and then it can calculate which segment should be downloaded independently of the server. So it doesn't have to wait for the server to update the index, and can fetch them directly without any delay. On the HLS side, things are a little bit more complicated, because in 2017 there was created something we now call community low latency HLS, when the community around HLS implemented something very similar and compatible with Dash. It didn't solve the index issue, but the segments were made fully compatible. Something I didn't say it previously was we have currently something called CMF, which is Common Media Application Format, and that allows us for Dash and HLS to share the media segments. That's for normal VOD streaming. That's for live stream. That's for normal latency live streaming. And community HLS also supported to have the same files as Dash over chunk transfer. But in 2018, Apple came, which is our original author of HLS, and presented a completely different, incompatible way to do low latency HLS, which wasn't very welcomed by the community, which didn't use chunk transfer. It used byte request and depended on HTTP to push requests. From that point, it changed. Currently, we are at the draft 13. That's from May of this year, and more drafts are expected, so it's not stabilized. And Apple is slowly coming to be Dash compatible, so we will see where it lands. The current state is Dash is widely supported, and you can use it anywhere, the low latency Dash, except on iOS. On iOS, if you want to have low latency, you have to use the Apple low latency HLS, or not in iOS in general, on iOS in browsers. And it's specifically iOS, even iPadOS supports low latency Dash. It's only iPhones. And we will see where this ends. So this allows us to shorten this part from waiting to the segments for 5 to 10 seconds to something under 10 milliseconds, which is great. But of course, nothing great is without problems, and this presents us with two main problems. The origin and storage has to support this, which doesn't seem that hard, but the standard implementation doesn't. Because if you use for storage something like AWS S3 object storage, well, you can't use it for this because it doesn't support reading before the file is fully written, and we need that. And it also doesn't support even to start the upload before you know the file size. And because we are transferring the file before it's fully created, we don't know the size. So we have problem at storage. And even if we use some normal POSIX block storage in Linux and use for origin some standard HTTP implementation like Nginx, most of those standard implementation like Nginx doesn't support that. They doesn't support reading file before it's completed because the servers doesn't know how long and if they should wait before the file is completed. They just read that the current size of the file, send it as it is, and doesn't wait for new appending of the bytes. So you usually have to ship some completely new implementation of the origin. Usually that serves it from memory. So the packager stores an origin sends it to the CDN, and after the segment is complete, it's then saved to some distributed storage. And the other problem is the CDN must support using in-flight data. So everything after the packager have to support that. With CDN, on the first hand, it doesn't sound like a big problem, but a lot of CDNs doesn't support that. If the CDN is built again on Nginx, which is very popular, Nginx doesn't support that. Varnish, for the other hand, does. I think Showmax used Varnish and currently switched to Nginx, if I'm not mistaken. The opposite. You switch from Nginx to Varnish. Okay, so Showmax guy is telling me that they switched to Varnish for live streaming. This will be probably one of the reasons. Yeah, they are telling, they saying yes. So yeah, you have to have CDN that support that. That's also not always the case because Nginx and a lot of caching proxies like that first download the whole file from the origin, and only after that can serve it to the clients. And now you have to serve the files, the bytes, as they coming to your caching your caching server to the clients right away. But yeah, this is all solvable problems. So we solved this problem. What's the next big number? Well, one of the problems is read-ahead buffer at the client. Read-ahead buffer is nothing more than the client is keeping some buffer in memory that it's intentionally playing behind. So it intentionally creates delay. That's mainly for being resilient to some network instability. If I am 10 seconds behind the live edge, I can any network disruption that's shorter than 10 seconds, I can retry. I can try to switch to lower bitrate. I am pretty resilient. So we can just eliminate the read-ahead buffer, but we create more problems, and the main one is we lose the time to recover when there are any network problems at the client. And the second biggest problem is we use buffer to detect adaptive bitrate switch. Usually when you have adaptive bitrate, you can watch your buffer fill and how fast are you filling that buffer to detect if you can switch to higher bitrate because you are downloading the files fast enough, or if you need to switch to lower bitrate because your buffer is becoming empty. Well, we practically eliminated the buffer, and we can't watch really how fast the files are downloaded because the limiting factor is not necessarily the network throughput, but if you are downloading 10-second file as it's being created, it will take at least 10 seconds to download. So you don't know if you have enough throughput to download a higher bitrate. This doesn't have any easy solutions. There are new algorithms Two of them are those two. I don't want to spell them for them, but this is still subject of PhD research. This is still not greatly solved. So if you want to have adaptive bitrate with low latency, mostly don't. or don't have the bitrate ladder you create, which can be for normal live streams. Have multiple steps. For low latency, you usually choose bigger steps and fewer steps with bigger gaps in bitrate, so the algorithms have easier decisions. And one of the things you probably will handle is catching up. If you want to keep someone at low latency, let's say 2-second end-to-end, what do you do when they have a network problem and get a spinner, get a loader, and download the data later? You can either skip the data to keep them at the 2-second latency, but that's not usually very acceptable. So you can play with the playback speed. You can play it just a little bit, just 5% faster, 5% slower, to either lower their buffer and catch them up to the live edge and keep the low latency. Or if you know the client has poor network performance, you can slow the player for them and create some buffer. Because you usually for the network problems doesn't want to eliminate the buffer completely, you just make it more dynamic. If somebody is at a good network, hardwired network at home, they can have very little latency. When someone is traveling with their mobile phone, you usually still have to get them some buffer so they don't constantly look at the loader. But again, those are problems that can be solved, and you can eliminate the read-ahead buffer. And if we skip over to the network part, because network is very complicated and no time for today for discuss the network. The next biggest problem with latency is transcoding. You usually won't implement your own transcoder. You will use something off the shelf, You will usually use some off-the-shelf transcoder. And most of the transcoders just have a switch to do low latency, which mainly means turning off features that adds latency, which is look-ahead buffers, B-frames, and stuff like that. Getting under 15 milliseconds is not really that hard because all NVIDIA encoders can do under 10 milliseconds per frame since for the last 5 years. AMD is around 16 milliseconds, I think. And most of the hardware accelerators and transcoders you will find are under 20. So if we have so many problems, there is a question, why not choose something completely different? Why not choose, for example, WebRTC as the low latency way to deliver stuff? And one of the points is HTTPC is well understood and supported. It's an old protocol. We have it for many years. It's highly optimized, have highly optimized engines, highly optimized clients, and you probably have to support it anyway. For free, with those, you get DVR, meaning delayed viewing experience, and VOD. So you can use the same media files you transcoded for this low latency for VOD later, and you can fall back to normal latency for clients that doesn't support low latency. Usually with just few tweaks to the manifest, you doesn't have to re-encode the media files. That's mostly important for use cases like social networks, because if you are a TV broadcaster, usually you have few important channels, so you can re-encode them with better quality later. But if you are doing social networks that have a long tail of many users with 0 to 10 viewers, you don't want to re-encode it again and again. So you can reuse the files the way they are. And most of the problems that I presented here today are the same for WebRTC. Those are not HTTP-specific problems, because you have to eliminate the read-ahead buffer and be more you are more susceptible. Sorry, my English today is not great. You won't handle great network problems, but that's not a problem of HTTP. That's a fundamental problem of low latency, because if you can have buffers, there's nothing to save you if the network goes down. Having re-implement origin and storage, if you use WebRTC, it's not very well established industry. You don't find many open source origin and storages for that anyway. And the transcoding is exactly the same for WebRTC. And it will be everything for me. That I was trying to make a point that HTTP low latency over HTTP is usable. You can use it today, and with the solution I presented, you can safely get under 5 seconds of latency, get a sub-second latency. You usually tweak the latency to trade-off between the stability and the latency. But the technology itself is very well capable of supporting sub-second latency. Any questions? I can either read the question back, or you can come here and.
Hello, Radek Zajíc. I have a question regarding the CDN edge. So, if Varnish is the only CDN software capable of delivering incomplete streams as they are coming in, do you run Varnish or Varnish-like CDN edge for live streaming with the low latency and Nginx for everything else? Thank you.
I'm not sure if Varnish is the only one. Is the only one I know of that has it built in. And no, we don't use Varnish. We actually have a custom version on Envoy or Envoy. I'm not sure how to pronounce that. So we have Nginx for the classic CDN, and for live streaming we use Envoy currently. Yeah, the question is, how do you cache not finalized requests because you can be sure if the content is correct? Yeah, well, I am not sure if I would call it classic caching, because it's more like a request coalescing for live streams, you usually doesn't even have to cache it somewhere on disk. That's why I won't call it caching, because usually most of the clients are watching the last segment, the live edge, and aren't watching with DVR. So when the segment is finished, you can usually throw it away. And yeah, you can validate that the files are correct. And you just have to live with that. There's no great solution. You can use protocols on the backend that are not HTTP and can help you with that. You can do in-band checksums. You can do in-band retries, because one of the problems is if like the request fails from origin and you have, for example, backup origin, usually you can guarantee that the files are the same from 2 separate encoders. Or as the CDN provider, we can guarantee that. We usually can't, from our clients that provides us that have their or own origins. We usually can't say that the data is byte by byte same, and there's also no great solution for that. If in the middle of request something fails, you just throw it away and start the whole request again, because anything else you will run into the problem that you are not sure if the data is the same, if data is correct, if getting those 2 byte slices one after another is even valid. And with H.264, H.265s, the decoders are pretty sensitive for any problems with that. So no solutions. Mirek, don't you want to come here so I don't have to? Because I'm thinking how to respond to you and also trying to remember word by word the question so I can repeat that.
I forgot my question. You mentioned the players. Do you know any open source player that would have implemented those getting faster or slower based on the buffer size? Because like I haven't seen that in open source yet, at least in Shaka. I'm not sure about Exa.
Actually, Dash group itself, Dash interoperability group, have a reference player for JavaScript, Dash.js, that implements ketchup and implements even those algorithms. And I think you can use that as a backend for Shaka, because it's mostly the backend. So Dash.js is probably the way everyone use it. I didn't see any new implementation because those two algorithms are not developed in academia. They have PhD papers, but are developed in the industry, and usually the companies itself, I can from top of my head say which companies provide the reference implementation, the Dash.js that everyone uses. And for ketchup, you also have multiple algorithms. One of them is the LOL plus. It also has a part for the catching up, and it's implemented in Dash.js. Maybe I can... show it to you. So this is Dash reference client, and it has implemented a bunch of options around that. So there's this ABR strategy. There you have catch-up mechanisms, and you can play with that. And this is used as a backend for most of the low latency players.
There is one more on YouTube, and I'm pretty sure you haven't heard that one yet. What does the 77 mean in your name?
It's just a random number. There are several theories of why it was created, but as far as I know, it's just a random number. I don't know. I am looking at Marek from. You write from CDN 77 saying it was on the only number for which was .com available. Okay, so that one I didn't heard it. I heard it's we make sites 77% faster. I heard it's some date meaning something, the date when someone was born. A lot of theories. That's maybe the most credible one. Any other question?
About HTTP3, are you already on HTTP3? Do you have some experience? Because I think it's quite widely supported now. And stable also engines support it. I don't know about Varnish.
Yeah, the question is if we are at HTTP3, if we support it.
And if you are, how's the performance?
We for Nginx for the part that's the classic CDN, we don't support it fully, and for the Envoy part we don't have a public offering of HTTP3 because we have tweaks, but we are using it internally for some clients. And the great part is for low latency live streaming is it's greatly improves the startup time. I didn't talk about that because usually you start the HTTP session, the HTTP connection, and then the overhead of establishing connection goes away because you keep the connection for the whole live stream, and you do request response pairs in those existing connections, but Quick mainly greatly improves the startup time. Also for us, it's a little bit problematic, and that's the way it's not yet public offering, because we have to optimize the performance a little bit more, because as it's UDP and it's in userland in Linux, the performance is not as great per CPU as with TCP. So for us, it's in the stages we are trying to implement and optimize it to do public offering of that. Any more questions? I don't see any, so that's a wrap.
So thank you very much. It was awesome.